Okay. Well, thank you all very much. It's my pleasure to be here and share some thoughts with you about how the field of information management has really been evolving. So I'd like to start, let's see if I can get the slides to go. Can you all see that? All right. In the early days of networking, when we first started, the challenge for us was interoperability, getting computers to interact with computers, and we considered the job from the point of view of a technology person completed when you took a packet from one machine and you successfully delivered it to the other. Some applications were built to make a lot of data move faster, like in file transfer and the like, and email came out very quickly, but the basic job was to get the information from one machine to another. The challenge, therefore, was how to make this interoperability sort of seamless and not terribly challenging. You didn't have to know where the machine was, what network it was on, how to do the routing, and so forth, what protocols to use. Unique identifiers were critical. There were IP addresses, basically, in that stage. But once the data got there, it was up to the users, typing on the keyboard, looking at screens to make good use of that capability. I was reading the European Interoperability Framework document that many of you may have seen, which outlines the challenges for interoperability today quite well. And these are systems that will not only handle big data and have AI capabilities, but virtually everything you can imagine that's informational. And so the real challenge today, as I see it, is how do you get different kinds of information systems to become interoperable when they're built by different parties to different kind of standards? What are the primitives that make that all work? And that's where the digital objects come in. So I'm going to tell you a little bit about what they are and where the current state of affairs is for dealing with that. Now, in the area of big data, this is really very significant because just having a terabit of data show up is not very helpful unless you know what the bits mean. So you've got to really know how to break them up into the relevant pieces, find out what they are, and so forth. And more importantly, you need to understand about how to deal with the very large storage activities. If you had a terabyte of data and all you wanted to do was go in and pick out a temperature reading or a cholesterol reading or something like that, you don't want to move a terabyte of data. You probably couldn't store it anyway. And so you need to be able to decide how you're going to process it, where you're going to process it, and so forth. Now, I've also been involved in a lot of the AI research funding for many years, and let me just tell you that the challenges there are equally as daunting, and in fact, somewhat more daunting, because now you've got to get into more of a domain understanding. You've got to understand how to deal with terms semantically and to disambiguate them. And of course, multilingualism is a pretty critical issue. Now, in terms of how you would do this as a practical matter, imagine now we're talking about multiple information systems that now need to interoperate. So it could be a banking system that needs to interoperate with a healthcare system, which needs to interoperate with an insurance company system, which needs to interoperate with pharmacies, which needs to understand what the lab results were, and they all were done by different parties to different schemas and so forth. How does that all work together from an interoperability point of view? Well, it's like the Internet Challenge, but it's one level up from that in my view. So focus in the Internet was on the protocols, the standards, and the global participation. It took a while to develop and put in place. Today, people understand how that's managed, but when they look at something new, they say, well, you don't have the standards in place, you don't have the management team in place, and that will all develop over time. But more importantly, if you were to talk to companies and say, what are your needs for interoperability, they won't know what they are today, necessarily. Some might, but most won't. But that was the same thing in the research community. If you ask them, why do you need a network, back when we first started, they really didn't know either. They were trying to explore. Could computers work with computers? But the funding agencies, and I was the principal funder at the time, was basically saying, look, we'd like you to put them in and go experiment with it. Write us research proposals, figure it out. That's what they did. So we have a similar situation today, except that in terms of what we're dealing with is information represented in digital form. We call these digital objects. There was an ITU-T standard on this whole subject matter called X.1255. You can find it. It's translated into something like 6 major languages. In that particular document, because they were using standard ITU terminology, they started from the notion of entities, which they said is anything in the physical world that has a kind of a unique identity. So, a person would be an entity, a car would be an entity, and so forth, but probably a water molecule wouldn't be, because you couldn't differentiate it from any other water molecule in the universe. And so whether we call them digital objects or digital entities, to me, it's really basically all the same. But the thing that makes a digital object is not that it's a sequence of bits, or even a set of sequence of bits, but that it's got a unique identifier associated with it. That identifier we often call a handle, as if a handle to a suitcase, if you like that analogy, or sometimes we'll refer to it by its longer string, digital object identifier. It could even be digital entity identifier. One of my colleagues here in Europe is involved in the Research Data Alliance, likes to call them PIDs, which to him means a persistent identifier. But there are a lot of brand names as well. So you would see in scientific journals things called DOIs, which is the shortened version of digital object identifier, but it's a trademark of the publishing universe for the most part. IDERs, another term that's been trademarked, it's used for the entertainment industry, and so forth. There is a core architecture for that. I view it as a logical extension of the internet, sort of providing some more infrastructural primitives that make it easier to deal with information. When you think about the capabilities you now have out there, you might think that initially we don't need anything more. We have databases, you can put your information into a database. We have the web, you just use the web. You have the clouds and things like that. But the fact of the matter is, if you took information in one database and ported it into another, you're going to lose a lot of the associated information that goes with it, the access control, provenance, and so forth. You really would like that information in digital form to be self-describing. So if a piece of information shows up on your machine, you know what it is, you know where it came from, you know what you can do with it, and so forth. And that's what the digital object architecture allows. So I'm going to say a little bit more about what that is, but this whole architecture was introduced into this European, American, Australian Research Data Alliance, which is looking at these set of issues for big data in a very basic way. And I introduced that at the very first meeting, and they've been really having at it intensely for, 6 years now. And so much of what was posed there, they didn't accept at first blush, because they said, well, we need to think about it. What are the alternatives? Maybe there are 10 different ways. And they've been coming back and saying, well, really, this is the minimum kind of representation you would want. And so they're really comfortable with that. So let's say a little bit about the architecture. First of all, it's got the same architectural feel that the internet did, namely it's open architecture, it's independent from the underlying technology, minimized complexity, it's non-proprietary, publicly available, there's no charge, and it's got 3 basic components. One, notion of registries, because if you have a digital object somewhere in the world, let's even assume you know what its identifier, it better be accessible from somewhere or you'll never get it. It's just a fact of life. And so what a repository is a way of managing access to these objects, but it's not about the storage itself. The storage can be anything behind the scenes. It can be in clouds, multiple clouds even. It can be in databases. It can be any way you like, making use of commercial or other storage technology. If you have a repository, you'd probably like to know what's in it, and those are called registries. They keep metadata about those objects. But if you don't know the identifier for an object, how do you find it? Well, use the registries to go search it based on whatever the de jour best techniques are, whether it's keyword matching or whether it's presenting an image and having it translate to something, or sounds, or whatever the best research ideas are, you can imagine modularly fitting them into a registry. In fact, as I'll say in a few minutes, we have some reference software, so people who want to get started exploring this actually have something to start with. They don't have to figure out how to invent it all from scratch. And so we put the notion of repositories and registries together in a kind of reference model, because the repositories need registries to know what's in them, and the registries need repositories to store the metadata. And then needs to be a global resolution system that if you've got an identifier, you can go from that identifier to the information that you're looking for in a pretty seamless way. So let me say a little bit about how that works and clarify a few things. First of all, many people, when they think about an identifier system, they're thinking there must be some central body that's creating identifiers and giving them out. That's not what this is about, any more than the internet was about one computer doing all the computers. Fully distributed system. Individual organizations can create their own identifiers, can create their own records for those identifiers, and decide where they want to store their information, and who can access it with full security. But if everybody were to identify everything with the same identifiers, or even two parties, how do you distinguish? If everybody numbered their digital objects, 1, 2, 3, 4, 5, how do you know it's this party's number 1 versus that party's number 1? And so the way we deal with that is by giving it a unique number for that organization. And so by looking at the identifier, you can figure out what organization must have created and then go ask them. Now, I purposely didn't say persistence, but one of the things that people are really concerned about, especially when identifiers get embedded in lots of systems, CD-ROMs and the like, you could have millions or billions of identifiers stored around the world, and you don't want them timing out. So if you look at the web, in the early days of the web, the URLs would break every few years. The half-life was maybe something like 5 years in the early days. I'm not sure what it is today. But you don't want something tied to a particular machine or a particular address in the internet, because these things can change. And so if you're dealing with, let's say, archival information, could be governmental information, company information, and it's stored in some fashion, and you can pull out the identifier, you'd like to be able to click on the identifier, or whatever the technology of the day is. Maybe you blink at the identifier, and it somehow goes and finds the information. In a completely different world, different communication networking procedures, different computers, and everything could be different, and yet the identifier and the information in digital form are linked in a persistent way. But to make it persistent, organizations have to manage the data. So, if you move it from one place to another, so the previous form of description, let's say it was a URL, doesn't work anymore, somebody needs to be able to manage that, and you don't want to go into 1,000 CD-ROMs and change them. You want those identifiers to still work even though the information is moved, and that can be done through this resolution mechanism. Now, typing is important, and so every element of a digital object is essentially a type-value pair, and the type says what the value is about. So if it's, let's say, a movie in digital form, you might have one thing that says this is the type audio, this is of type video, or it could be a sensor set of data in a big, large research data set. And so it will be chunked and fragmented, and you could say, okay, this type is here, maybe this is how far it goes, and so forth, so you can figure out what's actually in there. And if these types are actually identifiers as well, you can resolve those types to find out the description of what the type is, and you could have multi-language descriptions in there for people who don't want it in just one language because they maybe don't understand that language. So this is very important, and there's a group that we've been working with in ISO to come up with a standard descriptor of what a type record should look like. So when you got it, you know how to parse the type record. Now, in the field of AI in particular, I think we're going to see a need for people to build repositories of domain-specific knowledge, so not everybody has to recreate it. There's a real challenge there, and it's partly semantic, and it's partly just extracting it in the first place. But these can be managed as digital objects and made available not only for research purposes, but for use by products in the marketplace. So if you're selling a toaster, the toaster can learn that if you do something that's wrong, the substance could burn, for example, or learn that, whatever you're trying to learn about specific knowledge in that subject. So let's talk about scalability then for a moment. I'm assuming that every device in the Internet of Things, everything in the Internet of Things, is going to have information stored in it. Therefore, they're all going to be little mini information systems, and you're going to want to access the information that's in those devices. And those devices are going to want to interact with others. So these are digital objects that contain other information, maybe more digital objects inside, but interoperability becomes key. And you can imagine simulation systems that are putting together digital objects in gaming terms and the like. Well, if we really do have the kind of numbers of devices that people are now talking about, maybe 100 billion in the coming couple of decades, I'm assuming there might be 1 trillion repositories out there. Some may have only a very small amount of information, some may be big. I mean, the airplane is a big information system. Lots of different things, and they can all be structured as digital objects inside. So if somebody gave you an identifier, maybe it came in an email or you read it somewhere, so how do you go from that identifier to the repository that's got that information that's being identified? You're certainly not going to want to ask 1 trillion different repositories. Do you have it? Do you have it? And so forth. So you need a way to streamline that process. And that's where this notion of a global resolution service comes from. If you can provide that identifier to a global service and it says, okay, here's state information about the thing that you're trying to find, and maybe here are 10 places in today's internet you can find it, some network of the future. Maybe it's got information about what you can do with this object. Maybe it's got public keys, so it becomes a PKI infrastructure. Maybe it's got some notions of whether this is free or there's a charge for it, some things like that. Then it makes it a lot easier. But we found in the early days that virtually every organization wanted to create their own identifiers and wanted to manage their own records. Well, given that that's the case, how many of those local resolution services would there be? Today, we have open source software that people download, and they come back and they get this number from us that they can put into their identifiers, so you know it's coming from that organization. We have probably 1,000, 10,000 individual contracts. If every organization in the world and every individual, and who knows, wants to run their own, you might have perhaps 1 million local identifier services. So if you had an identifier, which of the 1 million identifier services did you now ask to find out which of the 1 trillion repositories to go ask? And so we broke the identifiers into this structure. There's a prefix. It's basically a number, a slash, and then a suffix. The suffix can be any identifier system you want, including legacy systems, new ones that you create. It could be cryptographic, semantic, numeric, whatever. But the prefix says what organization created it. And what we do is we retain all the prefixes. We assign them essentially, and they're given to an organization. They can use that from then on, and they can create derived prefixes from those prefixes. So let's say we had a number 1,000 as a prefix. We could create 1,000.1 or 1,000.abc, 1,000.computer science, 1,000.headquarters, whatever, and we can know about creating identifiers based on that because people will know who the organization was that created it. So we call this centralized registry of prefixes the Global Handle Registry. And the way you now resolve an identifier is first resolving the prefix in this global registry, then going to the local handle services, since you know who might have created it. They may say we didn't create it at all, and it goes from there. On the issue of finding identifiers, if you don't know what they are in the first place, that's where the registries come in. You search the metadata. So you want a document that somebody wrote 48 years ago on the following topic. Maybe the registry can tell you from the metadata, here are 3 identifiers that may be what you're looking for. Try them. But you're not going to find all the information in one registry. So there's a parallel issue here in federating registries so that you can learn a little bit about where that information is if it's not in a registry that you're normally used to dealing with. So, so basically every digital object and every identifier record is consisting of these elements, each of which is a type value pair, and so you can parse this record very clearly and know what it is that it's saying. Some of these types may be very well known and your system just has them embedded. Some of the actions that are associated with them, same thing. You can have multiple language descriptions and the like, but most importantly, users can also create their own type records and post them to the world so that you can learn about them at your own leisure whenever. Now, the thing that made the internet work well was we had a protocol that we developed called TCP/IP that made it possible not only to route the packets, but to have them understood when they got to the destination field. So we have a similar kind of thing here, but it's at the level of the objects themselves. So we have this model that the digital objects need to talk to digital objects, whether they're books in digital form talking to other books to expand their knowledge universe, or whether it's just a big information system talking to another one. Well, we know that airplanes need to communicate to avoid crashes, and autonomous vehicles on the ground need to, but what about cars talking to airplanes in case they want to land on a busy highway? What about a thermometer needing to talk to a heat control system and vice versa? So you need some way of interfacing, and it's one that we're using is called the Digital Object Protocol. And this digital object protocol is called Digital Object Interface Protocol. In the ITU report, it's called the Digital Entity Interface Protocol, basically the same thing. But it's very scalable because it interacts with the two ends of the two parties to this communication only by exchanging identifiers. Think about that. If you came back and you wanted to deal with a repository 100 years from now, 1,000 years from now, everything about the technology might be different. I can't even tell you how the bits would get there. But when they do get there, you want them to be able to be understood. So the detailed specification of this that's posted on the internet at a site called dana.net. You can see if you can see it. Yeah, there it is on that one. So one of the identifiers that's passed is the identifier for the target of your action. The other one is the identifier for the action itself. And if those are already embedded in, they just happen very quickly. But if they're not, then you can resolve them to figure out what the action is, download the program, and move on from there. So to get started with this, we have a notion that providing some reference software would be helpful. So there's a certain amount of identifier software. You can download something called handle.net from CNRI. It's available to everybody, provides local identifier and resolution services. The Dana Foundation, which I'll say one more thing about in my last slide, is a nonprofit foundation in Geneva that deals with places around the world, so this isn't a US-centric kind of activity. And that software does essentially the same thing. You can get this combined registry repository software. It's currently on the internet at the Quadra.org website, but this doesn't yet have the DOIP software in it. That's going to happen, I'm told, within the next 3 weeks or a month. So I would say wait 3 weeks and then download that version so you can experiment with the DOIP interface software. And there's proxy software that allows it to work with different kinds of private systems, such as the web. So if you were to provide a URL and that browser doesn't know how to deal with the handle system, the proxy will then convert it, extract URLs, and hand it back with redirects. And so that's what a lot of the publishing industry has been doing. A bunch of applications. I don't have time to go through these, but it's been used in supply chain management, for managing movie assets, food chains, counterfeit products. It started out with folks in the digital library field and the publishers. In fact, most of the scientific journals use handles to reference their articles. Sometimes they're trademarked versions, like DOIs are a trademark of the publishers, but sometimes they're not. Financial management system been built for managing options trading, tracking bonds, medical records, and interoperability of medical record systems, construction records in the UK, for example. They require that you maintain detailed requirements of building plans and I would say the things that go along with it, like the approvals, maybe the building codes, but also they want to know everything that's in the building, and we prototyped a system like that with this technology. Pharmaceutical information, so you have to put little packets of paper in every medicine packet that you buy. Telecommunications, I've heard presentations on how it's being used for cell tower management. In sub-Saharan Africa, there were folks in Rwanda who've been using it for managing real estate transactions. It's got built-in support for taking digital objects and linking them easily to other digital objects. So any of you who have read all about blockchains and think they're brand new, they're really not. They go back decades, in fact, and you can build some easy linking mechanism yourself, build your own equivalent of something like that if you think they're necessary, even run the whole thing in a system of your own with whatever chaining mechanism if you like. And I've been at some interesting forums in China where this is being pushed more top-down than bottom-up, but they've got a large fraction of their industry promoting and describing what they've been doing on a fairly regular basis. So this is really my last slide. The Data Foundation was a nonprofit that we set up in January of 2014 in Geneva, and the intent was to provide coordination, some reference software, and other strategic services for developing, evolving, and applying the DOA with the basic mission of promoting interoperability across different systems. They promote Recommendation X1255, and they deal with administrators around the globe. So they provide oversight like you might administer in airspace, but you don't fly necessarily the airplanes as well. There are currently 9 places around the globe that are doing the administration, including some in Africa, Europe. There's one here in Germany that's run out of Göttingen. We do the one in the United States. There are some in the Middle East and so forth. And one of the things it does in particular is it provides the overall oversight and administration of this global handle registry. I might say also that it's a challenge to anyone looking at this and saying, well, who needs this interoperability? But that's the same problem that we had in the early days of computer networking. Who needed computers linked together? We created a research challenge for that, namely figure out how you could get programs in one computer to work with others. There's been a lot of progress. The problem may never be solved completely. I say the same challenge exists here. If you're developing one kind of information system, you would like the ability to link it up with others without having to do a lot of conversion work and understanding, so you can just map between things that you can learn about through the appropriate registries. So I think there's a real potential here. I think this is as simplified a basis as you can possibly get. It is being adopted fairly widely, but it is not yet at the same level of penetration. It's going to take many organizations and companies figuring it out, and I think the lead is probably going to come from the research community, and particularly the Research Data Alliance is spending a lot of time looking at this. Peter Wittenberg, who used to be with Max Planck, is playing a lead role in the European community on doing that, and I actually think that industry has a lot to learn from the research folks looking at the big data initiatives, some of the AI issues, and they have a lot to learn from industry, which will probably find real applications now as opposed to longer term research applications. At the back of my slides, I'm not going to go through them, there's a set of background reading, things you might find interesting on 2 different charts, including one that traces the history of this stuff. It's a paper on representing value as digital objects, its relationship to the Internet of Things, and some early work that was done to try and put this into perspective in the context of mobile programs. So I think I'm over my time, so let me stop there and say thank you very much.